H2 molecule. Total number of electrons in H2 molecule. Total number of electrons equals to only 2 electrons are present. One hydrogen with every hydrogen with a single electron, so the total number of electrons equals to 2 electrons. And here molecular orbital electronic configuration can be written as these 2 electrons will go into the sigma 1s orbital, so its electronic configuration is sigma 1s2. Then bond order. Bond order equals to half of the number of bonding electrons minus number of anti-bonding electrons. So that gives the half of bonding electrons, 2 electrons are there, anti-bonding electrons are not there, so that it is equals to 1. That means there is a single bond between the 2 hydrogen atoms, and here both of the electrons are paired electrons, hence H2 is a diamagnetic in nature. Let us take the H2 plus. H2 plus means only one electron is present. So total number of electrons equals to only one electron. So molecular orbital electronic configuration is sigma 1s1, whereas bond order is equals to half of number of bonding electrons minus number of anti-bonding electron, that equals to half of 1 minus 0, that equals to 1 by 2. That means 0.5 bond order is present. That means bond is partially started forming. And magnetic moment, since here one unpaired electron is present, the molecule is paramagnetic, the ion is paramagnetic. Next, let us see the H2 minus. Total number of electrons. Equals to, each hydrogen contributes 1 electron, so that 2 hydrogens give the totally 2 electrons. Extra negative charge is present, so that total number of electrons in this molecular ion is 3 electrons. So let us write down the molecular orbital electronic configuration. Sigma 1s2, which is completely filled, still 1 electron is present. That goes to the sigma star orbital, sigma star 1s1. So that bond order now is equals to half of bonding electrons 2 are there, anti-bonding electron 1 is there, so that final bond order equals to 0.5. Since 1 electron is present, it is also paramagnetic in nature. Now we shall see that stability usually directly proportional to the bond order. If a bond order is same, then it inversely proportional to the number of electrons in anti-bonding molecular orbitals. If anti-bonding orbital electrons increase, then stability gradually decreases. If anti-bonding electrons remain same, then bond order depends. So mainly depends on the bond order. If bond order is same, then we need to consider the number of anti-bonding electrons. So that now let us check this. First of all, the order is bond length. So bond length, again here I will give the bond length is inversely proportional to the bond order. Higher the bond order, lower the bond length. So now let us go for these orders. Bond length, so bond length, if you see this, all these three, H2 plus bond order is same, H2 minus bond order is also same. So both of these are having the similar bond order. When bond order is same, then stability or the bond length depends on the number of anti-bonding molecular orbital electrons. So in the case of H2 plus, anti-bonding electrons are 0, but in this case one anti-bonding electron is present. That means it causes the repulsion, which causes the increase in the bond length, so that H2 minus bond length is more than the H2 plus, which is more than the H2. Next, bond enthalpy. Higher the bond order, more the bond enthalpy. So that here bond order is more for the H2, so its bond enthalpy is also higher. H2 is greater than. Next, H2 plus H2 minus same bond order is present. In such cases, lower the number of antibonding molecular orbitals, more will be the stability and more the bond enthalpy. So that H2 plus bond enthalpy is more than the H2 minus. Next, bond order. Bond order is highest for the H2, one bond, remaining two or half of bonds are there. So that H2 is greater than H2 plus, which is equals to H2 minus. Bond order is similar. So now let us take the He2 molecule, whether it exists or not. Total number of electrons equals to 4. Molecular orbital electronic configuration sigma 1s2, sigma star 1s2. Bond order, half of bonding electrons minus anti-bonding electrons, 0. That means He2 doesn't exist. There is no bond. Now let us see the He2 plus. Total number of electrons, 3. Molecular orbital electronic configuration sigma 1s2, sigma star 1s1. Bond order, half of the bonding electrons minus anti-bonding electrons. That means in comparison to He2, at least there is a chance for the formation of the half the bond in the He2 plus ion. And what about its nature? It is paramagnetic. Sixth one, He2 minus. Total number of electrons, 5 are present, and molecular orbital electronic configuration sigma 1s2, sigma star 1s2, sigma 2s1. Bond order, half of the bonding electrons 3 are there, anti-bonding electrons 2 are there. So here also bond order is 0.5. Since unpaired electron is present, it is also paramagnetic in nature. Now if you compare the stability of these ions with that ion, let us take the H2 plus, He2 minus. Let us write down the bond order. H2 plus bond order is 0.5. He2 minus bond order is also 0.5. Number of bonding electrons. In case of the H2 plus, only one bonding electron is present. He2 minus 2 plus 1, 3 bonding electrons are there. Number of anti-bonding electrons. So number of anti-bonding electrons, there is 0. In case of He2 minus 2 anti-bonding electrons are there. If you see the difference between the bonding electrons to the anti-bonding electrons, 1 minus 0, so 1, 3 minus 2 is equals to 1. So the difference value here and here both are same. That means when the difference values are same, both H2 plus and H2 minus has same bond length and bond dissociation enthalpy. So this is the way we can compare these molecules.